Good afternoon. Today we will cover the Unit 2 notes, slides 1 through 7. The topic of Unit 2 is solution stoichiometry. So we've already been practicing stoichiometry, which is using the ratio of coefficients in a balanced equation to make predictions about how much product will form or how much reactants are needed. This time we'll do the same thing, but in solutions. And you'll find that in solutions, there are different units and some different expectations that we need to learn. Many reactions occur in an aqueous environment, so we will frequently be talking about solutions that are occurring in water or aqueous solutions. Just a little bit of background information about water. I know that you probably recall water is H2O. Water is a bent molecule having the shape that you see here. The OH bonds in water are what we call polar covalent. Remember, covalent referring to sharing or shared electrons, but polar referring to unequal, right? So that between the oxygen and the hydrogen, the electrons are actually pulled towards the direction of the oxygen. And so sometimes we draw a little arrow to show the pull of the electrons, and then we put a plus at the butt of the arrow to show that it leaves the hydrogen slightly more positive since the electrons are being pulled towards the oxygen and leaving that slightly more negative. So our third bullet point, oxygen is more electronegative, thus the uneven sharing. So remember that substances on the periodic chart furthest to the top and right-hand corner are the most electronegative. Fluorine, in fact, is the most electronegative element on the chart, and oxygen is the second most. So one of the aspects of electronegativity is that it has a very strong pull on its own electrons and the electrons of other atoms that it may be bonded to. Bullet point 4, oxygen has a negative dipole moment, and hydrogen has a positive dipole moment. So that word dipole, right, di meaning two, and pole meaning opposing sides. So oxygen has a sort of negative temporary charge. It is not really a charge, so we call it a dipole moment. So at any given moment, there will be more electrons in the region of the oxygen than in the hydrogen. And this symbol, this lowercase Greek letter D or lowercase delta, that's the symbol that we use for dipole moment. So this symbol here letting us know that the hydrogen has a positive dipole moment, that the oxygen side of the molecule has a negative dipole moment, and the ratio, of course, for hydrogen is 2 of those electrons because 1 is coming from each. So that's why we have a 2 there. The last bullet point, water is, of course, then a polar molecule. It is a polar molecule, right? We can see that overall there is a negative pole and a remaining positive pole. It dissolves polar or ionic substances and strong acids ionize. And that's really what we want to talk about today. How is it that certain substances react in water in a predictable way? We have this saying, like dissolves like. So it's a well-known concept that substances that are polar, such as water, will dissolve other polar substances. And the reason why is because water has these charged moments. Even though the molecule itself is not charged, it has a tendency to behave like it is charged at various moments, and therefore it bonds well with other things that are polar or ionic, right? Things that have a charge. And we're also going to learn today that it has a special capacity with acids as well. Now, how again do ionic substances behave when they're in a watery environment? The lattice That is the name for the 3D arrangement of ions. The lattice of ions actually break apart into positive and negative ions, right? Those are the cations and the anions. Positively and negatively charged ions, and they evenly distribute in solution. The vocabulary that we use for this is that ionic substances in water both dissolve, meaning they mix with the water, but they also dissociate. And that is a unique word used specifically for ionic substances. Ionic substances dissociate. They no longer associate with one another. The pluses and the minuses come apart. We say that what is formed then is a strong electrolyte, right? Strong electrolytes include things like strong acids, strong bases, and ionic salts. So you may recall that an electrolyte is some liquid that can conduct an electric charge, and it's strong, meaning its capacity to conduct is very strong. And so when you put an ionic substance in water, you make an electrolyte, a liquid that can conduct electricity. Here are some examples of ionic substances and how they behave in aqueous solutions. The first one is NaCl. As a solid, this sodium chloride will then be dissolved in water, and what happens? The sodium cation dissociates from the chlorine anion. Both of them become aqueous, notice. They were solids before, and now we use the symbol AQ to represent the fact that they're actually surrounded by water molecules. So the solids become aqueous. And we will be writing equations like this, and that's one of the things that will become a difference from the left side of the equation to the right side. Those ions will no longer be solid. Often they will become aqueous, and we'll learn how to tell the difference as well. What about our second example? Magnesium chloride, the solid salt, in a watery environment dissociates to the magnesium 2+ cation, which is now aqueous, and the remaining chlorine anions, which are also aqueous. So notice these ions break into individual particles. Break into individual pieces or individual particles. So the Mg is one particle, and each chlorine is its own piece. I think that line is short because I was expecting to write ions on there. So you can write individual ions. Okay, it breaks into the ions. Let's take a look at the third example. How many ions is this third example made of? One aluminum 3+ ion and 3 of these nitrate ions. So that's a total of 4 ions. So on the right side of the equation, I am expecting 1 aluminum and 3 nitrate ions because we just learned that it will break into the individual ions. What else do we see? This substance goes from a solid to being aqueous. We see that. And we also see that the polyatomic ion does stay intact. So the NO3 does not break apart. Remember, what NO3 is made of is all nonmetals, an N and 3 O's, and the bonds here are covalent bonds. These are not ionic bonds. This is not an ionic substance. In and of itself, it's a covalent compound. So those bonds aren't simply going to come apart in water. We're going to see a little bit more how covalent substances behave in water. But right now, we're seeing a preview. They don't simply dissociate as ions do. And finally, we have a picture of a lattice. And this can be, right, any set of cations and anions in that 3D repeating organized structure. And when the cations and anions come apart, you see the water molecules there waiting to hydrate them. And let's draw what this should look like afterwards. So this is sort of the before, after. I should have the free cations disassociated in solution. I should have the free anions disassociated in solution. And then I should have the water molecules surrounding them. And I'm going to use a highlighter just to show how the water molecule kind of has this cool little shape. And excuse me, I like when this tool. And just show how when I have these waters, remember the negative side of the water is the oxygen side, and the positive side is the side that looks like the Mickey Mouse ears, right? The two hydrogen side. So how is this molecule going to orient itself when it encounters these ions? Will the negatives go together? No, 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 right? So the positive side will be attracted here. And as many water molecules as can fit will surround this ion in the orientation based on their attraction, right? So the positive sides will reorient themselves and turn around, and the negative sides, right? The negative oxygen side will be attracted to this positive cation over here. And I could do this over and over to show what is essentially called hydration. Hydration is when these ions become sort of surrounded by water molecules in an aqueous solution. Now, this is specifically, remember, for ionic substances, metal, non-metal substances that are becoming aqueous in solution. What about covalent substances? Remember, these are non-metal substances. And I'm using the word neutral here to refer to not acid nor base. So I'm using the word neutral as opposed to acids and bases. They have a special way of reacting that we'll see on our next slide. So solute molecules remain whole, intact. They remain intact. The pieces separate and distribute evenly and mix with the water, but the atoms do not break apart. There are no ions within those molecules, so the actual molecules themselves remain intact. Point 2 says that when we dissolve some some covalent compounds, not all, and certainly not the bonds, dissolve. So they do not dissociate. So the vocabulary word that we correlate with the behavior of a covalent bond in an aqueous environment is that it dissolves. So simply mixing with the water, but the atoms do not come apart. There are no ions. And the bonds between the atoms in the molecules also do not break. So dissolving is what happens. Some covalent compounds dissolve only. The bonds do not come apart, not the bonds. Covalent neutral compounds, not acidic or basic substances. And this includes mostly sugars and alcohols. So this is an example of an alcohol. Alcohol has an OH group on the end. And then the beginning is an organic looking molecule, something with carbons and hydrogens. So that's how you would recognize alcohols. And on tonight's homework, there'll be a couple of alcohols that you'll need to identify as covalent. And this is the general structure. It has an OH group on the end and something in the beginning with a carbon and a hydrogen. So it's an organic molecule. That means it contains carbon, but it also has that OH group. Here's an example as well of what we have, a sugar that is a solid becoming that same sugar that is now aqueous. But notice the carbons, hydrogens, and oxygens are still intact. This molecule did not break apart. Nothing was released in the water. So that's very different than what we saw before. No aspects of it broke apart, just mixed in. And then the picture of the bottom, this actually shows some hexane molecules. And so if you can see, this is one hexane molecule, some carbons and hydrogens here, and it's covalently bonded. Here's another hexane molecule, and the red stuff at the bottom is a water. So over time, as we shift from the picture on the left to the picture on the right, we see hexane molecules can slide down into this water, and they can become dissolved, meaning they're mixing in amongst the molecules, but they do not dissociate. There are no ions. The atoms don't come apart. And in fact, specifically for hexane, because its density is so low, it will eventually slide back up to the top and even become physically separate. Now, the last category of molecules we need to talk about today are covalents, but this time they are acidic or basic as well as being covalent. So, covalent acids and bases in aqueous solutions. So remember, the neutral molecules are pulled apart this time, and actually broken into charged pieces. So that's something new. We have not heard that before. Let me read that again. Even though these acids started out as neutral molecules, they get pulled apart and broken into ions. They were not ions, they were covalent, and now they are ions. So while they do dissolve, and anything has the capacity to dissolve, right, particularly polar substances and water, they also ionize. We do not use the word dissociate because it's not merely a group of ions that are no longer associating with one another. We use the word ionize because they go from being ions atoms with no charge, non-metal groupings bonded to each other, to being separate ions. So they actually become ions through the process of being dissolved in the water. So they really get ionized. Here's an example. Now, remember, an acid has a hydrogen connected to some negatively charged anion, something that's going to pop off and become an anion. It's not an anion when it is together, but it will become an anion. So this is sort of a generic way that we represent acids. We put an H and the letter A. The H represents the hydrogen that's always leading. It's written first. And the reason that we write it first, specifically for acids, is because we expect that in an aqueous solution, which is most solutions, that hydrogen is going to come off and it will become a hydrogen ion. And the remaining parts of the acid will become a negatively charged anion, negatively charged, so we just use the letter A. So that's just a reminder about what acids are. Acids are substances that, even though they're covalent, they have a hydrogen. It is written first, and in a solution, that hydrogen is expected to come off, particularly in aqueous solution. Here's an example of a very famous hydrogen, hydrochloric acid, right? It is stomach acid. And in this particular case, it's starting out as a gas. But what happens is it will, regardless of whether it was starting out as a solid or a gas or even a liquid, afterwards, the individual ions will become hydrated. They'll break apart into ions, form ions, and then become surrounded by the water molecules, so we write them as aqueous. So it sort of behaves very similarly to an ionic compound, but one of the differences was it was not made of ions in the beginning. Here's an image of how a strong acid behaves compared to how a weak acid would behave. We say that a strong acid is strong because the full amount, so this bar sort of represents the full amount of the product, will become completely ionized into all H's and all A's. Every single one will separate. So your solution will have a lot of charged particles. So again, we call it a strong acid because it will be a strong electrolyte. Strong meaning it will become a strong conductor of electricity. So we call these the strong acids. And we're going to be learning a lot about strong acids. Now, on the other hand, if an acid is weak, by the way, hydrochloric acid is a strong acid. But on the other hand, if an acid is weak, such as vinegar, household vinegar is an acid, but it is a weaker acid, what that means is, and not that the concentration is weak, but it means that when that acid is put into a solution with water, most of it's just going to stay intact. When you mix vinegar with water, it stays vinegar. It just becomes kind of dilute. Some of the hydrogens come off. Yes, that's true. Some of the remaining parts come off and form negatively charged anions. But the majority of what was in that solution to start with remains an intact covalent compound. And while you can use the term dissolve, meaning that it mixes with the water, it does not ionize, it does not dissociate, the particles do not come apart, and it does not become hydrated with water either. So this, we would call it a weak electrolyte, because if you try to run an electric charge through it, there would be very few positive and negative charges to help propel that charge through the solution. So strong versus weak there. Now let's talk a little bit about electrolytes. Remember in the past, probably sophomore year, you did a lab with various beakers of substances and you added a light bulb to them, right? Probably put some electrodes down into the water, and then on the top there was a light bulb. And when you put it into the strong electrolyte, that light bulb glowed brightly. But if you put that same light bulb into a weak or non-electrolyte, right, it either glowed more dimly or not at all. And that's what we mean by an electrolyte. An electrolyte is a substance that is liquid and allows electric charge to be conducted through it. And you can see why, because there are charged particles in it. And so if it's a strong electrolyte, many charged particles are in it. And so it can light a bulb very brightly. If it's weak, it has only a few charged particles. And if it is a non-electrolyte, it has none at all. Now that, of course, depends on what we see here at the left, how many particles are in the solution to begin with, or if that thing that was added to the solution is perhaps not at all soluble, not at all dissolving, and it just kind of stays in a chunk and doesn't even break apart at all. So the nature of a solution and its concentration will dictate what chemical reactions take place. So that is why we are learning this. We need to figure out what substances, when you put them in an aqueous environment, will come apart, what will dissolve, what will dissociate, and eventually what will ionize. If a compound is highly soluble, right, that means it's either ionic, or it's strongly polar like these acids. And that's kind of the part of the secret to these acids, is that they have hydrogen in them that can be strongly polar and it can pop off in the water. A solution's conductivity depends directly on the abundance of ions in solution, right? It depends directly on how much concentration, the abundance of ions in that solution. Let's talk a little bit more about strong versus weak electrolytes. And this is also our last slide for today. So thank you for hanging in there. Strong electrolytes, remember, are strong because they conduct current efficiently. They light a bulb brightly. Whereas weak electrolytes, on the other hand, do not. Are poor conductors of current, and they light a bulb weak or poorly. All right, and here are some examples of strong electrolytes, and we'll have to memorize these. Strong electrolytes are any soluble salt, so that's a metal, nonmetal, that can dissolve in water. A salt is an ionic compound, so that's a metal and a nonmetal that can dissolve in water. Strong acids, which we will need to memorize, and strong bases. So salts, strong acids, strong bases. If the salt dissolves, strong acids and strong bases. Remember, the salt is a metal and a nonmetal. The metal and the nonmetal should come apart and form ions and be rich in solution. Remember, an acid is a hydrogen and something covalently bonded to it. The hydrogen should become, a cation. Whatever was bonded to it should become a free anion. And it turns out that strong bases are ionic, so they behave exactly like ionic compounds. Weak acids, on the other hand, and weak bases form weak electrolytes. And we'll see what those are on the next couple of slides as well. All right. Oh, excuse me. I'm sorry. We have two more slides. Slide number 9 is our last one. So you see the title of this slide, Acids and Bases to Memorize. You will need to memorize. The 7 strong acids are, right, they all start with a hydrogen, right, because acids all start with a hydrogen. It's written furthest left to remind us that in an aqueous solution, it will ionize and come off. So the first one is hydroiodic acid, sulfuric acid, hydrobromic, hydrochloric, nitric, chloric, perchloric. So these are the 7 strong acids, and it will be helpful to memorize these. You won't have to look them up all the time, and things will go much more quickly. Notice that they all start with an H, and then the anions that are connected to them form a fun little sort of acronym that I like to call isobroclo, no clo-clo. So if you can remember isobroclo, no clo-clo, then you can write out the acids pretty easily, knowing that they all start with a hydrogen, and then it's hydrogen with an I, hydrogen with a so, bro, clo, no, clo-clo. H2SO4 is actually sulfuric acid. It's the strongest acid known to man. There's a limerick: my father was a grand old man, and now he is no more. For what he thought was H2O was H2SO4. So that's a way to help us remember H2SO4's formula. SO4 is the sulfate ion. So a couple ways to remember them. All of the other acids are weak. So if it's not one of the seven, it's weak. If it starts with an H and it's not one of the seven, it's a weak acid. And so that includes hydrofluoric acid, sulfurous acid, carbonic acid, nitrous acid, chlorous acid, and hypochlorous acid. So those are some really common weak acids. But again, if you can memorize the seven, then you know that everything else that starts with an H is a weak acid. What about strong bases? Strong bases are called metal hydroxides because they're always a combination of a metal and a hydroxide ion. So any metal you can think of: potassium, rubidium, cesium, calcium, aluminum, magnesium, manganese, any of them, and put a hydroxide behind it, those are all strong bases. And one of the things you'll notice, hopefully, is that these are also metal nonmetal compounds. So strong bases behave like salts because they technically are salts. They're salts that contain an OH, and it turns out that when an acid and a base come together, the acid releases the H, the base releases the OH, and they make a neutral solution that is HOH, or water. So that is why a metal hydroxide is always a very strong base, because it will react with a strong acid to neutralize it and make water. Weak bases, on the other hand, only include nitrogen, NH3, NH2, and NH3. So weak bases are what we call derivatives of ammonia. All other bases are strong, so you will have to try to recognize anything that is NH3 or a derivative of NH3. So that's a compound with just an N or an NH or an NH2 or an NH3. All other bases are strong. And here's a little example as to why ammonia and its derivatives are bases, even though they are weak bases. So they don't particularly form water with an acid like the other ones we've seen. But based on this structure, one of the things that you'll see is that nitrogen has a tendency to form up to three sharing bonds, three covalent bonds, and then it has a free pair of electrons. And that free pair is ripe to match with a proton, a hydrogen ion. So when an acid gives up an H plus, this nitrogen is likely to take it, right? And so it can react with an acid in such a way that it'll take its hydrogens, but it'll only take some of them and it won't produce water. So it is weak, and so it will form a weak base then. Here's another example of an ammonia derivative that you need to recognize. So it has the NH2 grouping here. That's one of the derivatives of ammonia, but it's combined as it can be with a organic substance, something that contains carbon and hydrogens, whether it's C2H6 or C3H8, it's still a series of carbons and hydrogens with that ammonia or ammonia derivative on it. So these are the four categories that we do need to memorize, especially those strong acids. And we don't have to memorize the strong bases as much as we need to be able to remember that it's a metal hydride. All other acids are then weak, and then we will need to memorize the weak bases. So we'll know all other bases are then strong. Finally, non-electrolytes. So non-electrolytes do not conduct current in an aqueous solution, right? No electricity. There are no ions present in the solution. They may dissolve from chunks into molecules, but the molecules have no charge and their atoms do not separate. And so here's an example of a light bulb that is not lighting at all, and it is because in that solution you may have molecules, but those molecules remain intact. They do not separate into atoms, and there are no charged particles at all. This is a non-electrolyte solution compared to lighting the bulb or lighting it brightly, where we have ions in the solution. Remember, those ions are the product of either acids ionizing or ionic substances, including strong bases, dissociating in the solution.